Today's video, it's all about dismantling this variable frequency drive. So what the aim is, I want to get some scrap metal out of it so I can melt down, but also to scrap the electronic components that may be useful inside it. And it will be interesting to see when I dismantle it to see why this was thrown out. Before I dismantle this variable frequency drive, we'll have a look at the specs. So this is the input, and it's got 3-phase at 380 volts to 500 volts. And then you've got 50 to 60 Hertz. It doesn't matter what the frequency is because it's changed to DC, rectified. But here is the most interesting part for me. It says 180 amps AC at 400 volts. So that tells me there's going to be some really large diodes in there, which is what I'm after. So we'll go across to the output. So it's got 3-phase output and it goes to 180 Hertz. Now normally a 2-pole motor spins at 3000 RPM, but at 180 Hertz that is going to be well over 10,000 RPM. So that's really spinning for a motor. Be interesting to see that if it lasts. Here are the heavy duty terminals, and they've got the letter U, V and W, and what that tells me is that must be the output. And then I'll show you what it looks like on the motor. They always have those same letters on there to show you where to connect the terminals and wires to. Here is a cover off a 3-phase motor, and it gives you the instructions on how to connect it up, and you'll see you've got U1, V1 and W1, and you can see that that goes straight to the VFD. So what we're looking at then was the output of the variable frequency drives. So we've identified those output terminals, but there's 2 more on the right hand side, and one has got negative R and then positive R. Now what they're for, I'm pretty sure, is for the DC braking for the motor. So here are the input terminals. There we've got L1, L2 and L3. So next to those live 3 terminals, the input, we've got negative UZ and positive UZ. So obviously there's some sort of connection for DC to come into here. This is the controller. So what happens is you can connect a remote operated keyboard through these terminals and program the variable frequency drive. So we'll just pull it off. So what I'll be doing in this video, I'll be unscrewing all the screws and take the covers off camera, so it speeds up the video a bit. So what we've got the covers off, and we've got all the capacitors here. We've got the really big capacitors over here. Now these have got, I think, a bleed resistors on there, so they should be safe to handle, but I can use a multimeter to make sure that they are safe. And also I'll have a look over to there, and you'll find there's a lot of screws missing here and here and here, and other ones over the other side. Now I think what's happened there is the technician started to dismantle it, and then the customer probably said, no, it's too expensive to fix, I'll buy a new one. So they sort of dismantled it and let it go. So we'll have a look at the capacitors. They're not swelled up on the tops there, they look okay. So we'll flip it over. No burn marks on the printed circuit board, so we'll be testing those capacitors later on. So this is the first chance we've got to identify the scrap metal. We've got that one, and that one. So now we need to identify what the scrap metal is. So we've got here the bus bar, and this is the lifting eye. So I suspect that's been plated. I thought it was chromium plated, but here we got a magnet, and watch what happens. very weakly magnetic. Now it could be that it is tin plated, silver plated or zinc plated, but neither of those metals are magnetic. Only nickel is weakly magnetic. So we'll try this one here. It's magnetic, it's weakly magnetic. But the interesting part about this one here is it's magnetic there, but when you put it over to this side here, it doesn't quite want to pick up the magnet. So for this one here and possibly this one here, we'll grind off with the angle grinder the plating and we'll see what's underneath. It should be copper. So did you notice the difference? This one here created a lot of sparks, this one did not. And you can see it's copper underneath. Here is a close-up. You can see it's very thick plating and the very edge there's copper. And you can see with the lifting eye there's no copper plating underneath and it produced sparks, so the safe bet would be that it is stainless steel. So we'll try it again. Here's some more bus bar and there's the magnet. See, it picks it up. So what can we use this scrap metal for? It's got nickel plating on it, so what I need to do, if you really don't want nickel in it, you'll have to grind all of that off so you get pure copper. But the other thing you can use it for is tin bronzes really like nickel, and if you add nickel to tin bronzes you get a lot of higher tensile strength, especially with superheated steam fittings. I've used it for that. So this metal, if you get it, save it for mainly for high strength tin bronze. It's very useful. This is the part that I'm most interested in, is the bridge rectifier. And what I'll do, I'll test them on the bench and show you how I test them. This is the 3-phase bridge rectifier out of the VFD, and I'll show you an easy method for testing them without using a meter, and also we'll do a close-up of the specifications so it'll show you exactly how to connect them up correctly and also to make sure that the diodes are working. This is the close-up of the diode specs. So the first thing we'll look at is this number here. This is the part number. The 260 means it takes 260 amps, and the 16 means it's 1600 volts it's rated for. So the first thing what I'll do, we'll test it from here. You go through here and it'll go through the diode there. I'll use an ordinary 12 volt light globe, and if it lights up it works, and then I'll reverse the connection, it shouldn't light up. And the same for this one here. You go from here to here and you connect it to there, and you can test the second one. And the third test I'll show you with a meter. I'll show you the voltage drop it gets going through those two diodes there. So for this test we're just going to use 12 volt battery, and we're going to test this diode across here. So I've connected the negative from the battery to here, and then we'll just touch that. We can see it lights up. So what we'll do, we'll reverse the leads and we get nothing. So that diode is okay. So we'll test the second one, and there we got the light, works. So tested the second one. Now we'll reverse the leads again, go across to here. No light comes on. So both diodes are working perfectly. This is the meter test. So what we'll do, we'll put a probe on here and a probe on there, and we get 0.366 volt. Now to test if the diode's blocking the reverse direction, we just reverse the leads, and there's nothing. So that one's working okay. So what we'll do, we'll go across to here, and that's the second diode. And we just reverse again, and it's working. Now the interesting part is going across to here, you should see about 0.7 of a volt. So it's going through two diodes, so it's dropping the voltage to twice the amount. Before I actually touch or go anywhere near those big capacitors, I'll use the meter and we'll see if they're completely discharged or not. Yep, 1/4 of a volt, so they're safe to handle. So what I'll do, I'll test these on the bench and we'll see if they're any good or not. This is the first capacitor. It's rated at 850 volts. It's 90 microfarads. And there's the important dimension where it says plus or minus 10%. So it could be either 81 microfarads or 99 microfarads. So we'll measure one and we'll see what we'll get. So the meter is connected to microfarads, and what we'll do, we'll connect up the capacitor. And what we got? 88.9, so it's well within specs, that capacitor. This is the next test I'm going to do with electronic components, and I've got a variac, so I can slowly ramp up the voltage to test the two components. So this is what I'll be testing. Now there I've got those power blocks, the diodes, single phase coming in there, so you only need 2 blocks, and if you've got 3 phase you need 3 of them. So what I'll be doing, I'll be testing that capacitor as well. And the problem with the tests what I've done with the diodes is they're only low voltage tests, so this one's going to test it up to about 330 volts. So this is the big test. Now I've got a light globe to discharge that capacitor, and you'll see off the bridge rectifier I've got black coming to here and red to there. The red is positive and black is negative. So what I'll do, I'll bring it up slowly to the maximum voltage I can get from that, and I'll switch it off and we'll see how quickly it discharges, and I'll probably put another capacitor on to compare it to see if they're any different. So 57 volts, you can see the light globe starting to glow. It's 160, 200. So we've got 337 volts. Now what I'll do, I'll switch off the variac and I'll be able to tell with the clock on the camera, we'll see how many seconds it takes to discharge that 5-watt globe. So I'll switch it off now. That capacitor took about 3.5 seconds using the 5-watt globe as a discharge resistor. So what I'll do, I'll put another capacitor on and compare the times. So this is the second capacitor. So what I'll switch it off again, the variac, and we'll see how long it takes to discharge. This capacitor tested out the same using the 5-watt globe as a resistor. It was about 3.5 seconds. But you can see the bridge rectifier, that's worked up to 337 volts, so it's worked really well. I don't need to take it up to 1600 volts, that's a scary voltage. But also you'll notice all the bare wires around there, you have to be extremely careful when you test all this stuff. Now, going back to the capacitor, this capacitor hasn't got the polarity like other capacitors have got. So what happens is you can connect positive onto any terminal and negative onto any terminal and it will work. As long as you drain the capacitor completely, you can swap around those connections and it'll work perfectly well. But the next capacitor I'm going to test is the electrolytics, the black ones. They have to be the right way around. Do not ever connect them around back to front like I did one time. There's a lot of smoke and flames come out of them. So the black electrolytic capacitor is up to full voltage, 336.5 volts. Now when I switch off the variac, the light will stay on for a long time. I'll explain afterwards why that is so, but we still have to do the same test, so we're switching it off now. So that capacitor took 19.5 seconds to discharge completely. So why did this capacitor make the globe run so much longer? Well, it's all about capacity. You have a look here, it says 820 microfarad. The previous capacitor we tested was 90 microfarads, so this one is about 9 times larger. So it'll store a lot more energy. Even though it's about half the voltage, this one is 450 volts and the other one was 850 volts. So in reality these capacitors with the high microfarad rating are far more useful than the other ones. So these three transistors here control the DC braking, and that goes off to the negative rail and over to your motor, so you can slow the motor down. So with the chopper transistor, this is out and that's in. I'll take it out. So here we go, we've got everything stripped off. By the looks of it, I can see there's a half bridge there and half bridge there. So for that part there, that's one phase. Two more here, that's the second phase, and two more, that's the third phase. So that's what changes your frequency, and you can change the speed of your motor. You can see here we've got the current transformers here. They measure your current, I think it's for overload, and you can see the outlets here. There's your three phases. And you can see how they're tied together. There's two there and two there, so the outputs are tied together. So that's one phase and the other one's the second phase, that's the third phase. We'll have a look at the nickel plated bus bar. There's quite a bit of it. And the tally came up to 5.7 kilograms, and also the cable in the background is about 200 grams. So with this nickel plated copper, it's very thick, so when you melt it down you probably get a good 0.5% to 1% nickel addition to your bronze if you make bronze out of it. Here is the aluminium, mostly extruded. It comes to about 24 kilograms, and a couple of pieces of sheet aluminium there. I don't like using this stuff for casting because most of my castings need to be machined. So if you use this metal for making castings where you've got to machine extensively, you'll have to use lots of oil and it doesn't cut really well. Here we are at the end of the video, and what I've done, I've put all the capacitors in parallel. So we'll see just how much energy is in the capacitors when they're in parallel. And I thought it'd be a bit boring to use a light globe because it'd take about 10 minutes, maybe even 15 minutes to discharge. So I'm going to discharge it all at once. Now this can be a bit dangerous, so I've got to wear hearing protection, use gloves and use a face shield when I do that.